When table salt is dissolved into water, something odd happens. It splits up into the particles out of which it was made. It turns out that these particles, called ions, are the charged particles that atoms become when they gain or lose an electron. Because of their charged nature and freedom to roam anywhere in the solution, these ions can transfer electrical charge by moving through the so-called electrolytic solution, thereby forming an electric current in much the same way electrons do when moving through a metal wire. Since the movement of these ions through the solution forms an electric current, it is not unreasonable to think that the movement of the solution itself may influence this electric current. Although the current through an electrolytic solution has been described mathematically in a multitude of ways, I couldn't find any existing literature in which flow speed was considered. Because of this, I had to gather my own data. My test setup consists of 3 electrode gratings, which are custom gold-plated printed circuit boards mounted in a PVC tube using some flanges. They form a measurement chamber which I have dubbed the flow cell. A strong pump is connected to this flow cell in order to pump an electrolytic solution consisting of table salt in water through the flow cell from the storage container to the collector container. A power supply applies a voltage over the flow cell, which is monitored by an oscilloscope along with a current through the solution using a current amplifier. I ended up not using the third electrode. Every measurement cycle begins with a thorough flush of the measurement setup to make sure the solution is mixed as well as possible. After this flush, 3 measurements are performed. In all of them, a voltage is temporarily supplied to the electrolytic solution during which the current is monitored. During the first measurement, the solution is static. Because of this, I have called it a normal measurement. The second measurement is performed while the solution is flowing through the flow cell, which made it the flow measurement. The third measurement is a bit special in that the pump is turned on halfway through the measurement, so that I called it the disturbed measurement. I didn't end up using it for the analysis, but it does help to verify that an effect is present. I repeated these 3 measurements for a host of different flow speeds. For added repeatability and to save time, I automated the entire process. Here's an example of a disturbed measurement taken straight from my oscilloscope. You can clearly see the jumping current right after I turned on the pump. What's happening here? To understand this, we first need to know a little bit more about what happens when we apply a voltage to an electrolytic solution. Before we apply a voltage, the ions are mixed homogeneously. When we do apply a voltage, the negative ions are attracted to the positive electrode and vice versa. Because of this, the ions slowly start moving towards the oppositely charged electrode, only hampered by the drag they encounter. You would think that this creates a huge separation of ions throughout the solution, but what actually happens is that the ions clump up close to the electrodes, thereby negating their charge, so that the ions in the bulk of the solution aren't influenced all that much. This cloud of ions close to the electrodes is called an electrical double layer, and it is what causes the current to start out relatively high and then taper off towards the end. You may be wondering now where the base current comes from, since I just said that the ions, which transfer the electrical charge, stop moving after a while. This current arises from particles, which are bumped all over the place in a process named diffusion. They react at the electrodes in a redox reaction, thereby gaining or losing an electron and then diffuse away. Since they basically stole or brought an electron, charge was moved, thus creating an electric current. This current is known as the Faraday current. We can use an electrical circuit which was already known to model the electrolytic solution. These coils are resistors which hamper the current. This middle one resembles the resistance in the bulk of the solution, and these two model the Faraday currents. These two lines form a capacitor, sort of a rechargeable battery. It is used to model the build-up, or charging if you like, of the double layer. You may have noticed that the circuit is symmetrical. This is because the upper and lower capacitors and resistors both model the effects at one electrode. When you go through the math to find the response of the circuit, which I will spare you for now, you will find something that rather looks like our experimental data when plotted. The shape of this plot will change when the component values change. Using a computer algorithm known as the least squares function fit, we can fit the theoretic response to the measured data. We can then sort of reverse our calculations, which unfortunately isn't as easy as it sounds, that's another page of math for you, to calculate the component values from the shape of the function that our function fit determined. You would expect that in a flowing solution, some charge of the double layers would leak away. This would manifest itself in another path for the current to flow through, which is analogous to adding a resistor in parallel with an electrode. This would show up as a decrease in the resistance of the Faraday resistors. When we plot out the decrease in this resistance versus the flow speed, we do find that the resistance decreases more with higher flow speeds. What is unexpected, however, is that the double layer capacitance also changes with flow speed. More research is needed to find out why this is the case. That's all fine and dandy, But why put so much effort in some obscure corner of physical chemistry? Well, this effect could be used to design low-cost, non-mechanical, ultra-low power flow sensors which may have a longer surface life than their mechanical counterparts. Furthermore, this technology could be shrunken down dramatically to form arrays of flow sensors which may be useful aside from being insanely cool. If I were to do this research again, I would gather the data in a split stream to get a better fit between measurement conditions. I would also try a different approach to the analysis. By using alternating voltages, the response of the circuits at different frequencies could be studied, which could help speed up measurements and more directly calculate the component values. Anyhow, you just watched a visual summary of my profile project, Flow Dependency of Electrolytic Resistance. If you'd like to learn more about it, feel free to download it at my site. Thank you for watching this video and have fun exploring the world.